Welcome to this second lecture on power system dynamics and control. In the previous class, we had focused and discussed one important phenomena, that is the loss of synchronism. We will continue the theme of describing certain stability phenomena in a power system in this particular lecture. So, in this particular lecture, we will cover some other phenomena like voltage and frequency stability. It is a brief overview. The next 40 lectures will actually focus on all the nitty-gritties of this particular phenomena. Just to recap what we did last time, we discussed the structure of power systems. That is, we saw that most of the typical large power systems which are there today are synchronous grids. That is, they consist of a large number of large synchronous generators interconnected to each other by AC lines. So, once we have interconnection by AC lines, we discussed this, that in steady state we ought to have frequency same throughout, it should be the same throughout the grid. One of the problems, of course, which we are likely to face is that although the frequency should be same throughout the grid, under some large disturbances or large power transfers, you may have loss of synchronism. So, normally synchronous machines which are connected by AC lines tend to remain in synchronism because of the nature of physical laws, which of course, we shall discuss later in this course. Loss of synchronism is an important phenomena. Today, we will learn two other phenomena, that is frequency and voltage instability, and to do that, we will illustrate a few simple examples. First of all, let us answer the questions which were asked in the previous lecture. How many synchronous grids are there in India, or maybe in your country if you are not of India? How many HVDC links are there? How many of these HVDC links are synchronous links embedded in the synchronous grid, and how many of them are asynchronous links? So, the answer to this question is as follows. India is at present, that is in 2009, divided into two synchronous grids. The southern part of the peninsula forms one synchronous grid, that is, the synchronous generators in this part of the system are interconnected to each other by AC lines. The second grid, synchronous grid in India, is the rest of the system. The rest of the country is actually another synchronous grids. So, if you start off with one generator here, say at Trombay, and you follow the AC line paths, you can go to another generator in the same system, synchronous grid, through only AC line paths. So, all the generators in this northern part of the grid are actually in synchronism in steady state. So, they run at the same electrical speed in steady state. Of course, there are asynchronous links between the southern grid and the other grid. So, for example, there is an HVDC, long distance HVDC link from one state to the other. Here it is between Talcher and Kolar. Then there is another just here, it is a very short, it is called a back to back DC link, it is an asynchronous link. There is another here, these are all asynchronous links. So, these are asynchronous links connecting two synchronous grids. So, these two grids actually can be at different frequencies. Of course, there are HVDC links which are embedded in the AC system. For example, there is a HVDC link within this grid embedded within the AC system. It is a long distance HVDC link. So, there is in fact one here, there is another here, there is a short distance link here. So, this is the Chandrapur Padgha link, this is the Rihand Dadri link, and this is a short link which is actually not used for long distance transmission. These links, although they are present in the synchronous grid, they do not really cause you to have an asynchronous grid. However, these are asynchronous grids with controlled power flow. the power flow on these links, DC links, does not depend on the phase angle here and here. That is an important thing about the interconnects between these two regions. In this region, you have got a lot of AC lines, in which power flow of course is a function of the phase angular differences of the voltages at the two ends of the line. Now, just to illustrate the fact that we have the same frequency prevailing all throughout the grid at a given amount of time, all throughout a synchronous grid, I shall just show you a snapshot of the frequencies reported on the websites of the load dispatch centers at various locations within the country. In fact, I will show it to you at 3 locations. All these locations are more than 1000 kilometers apart. So, you see this is a screenshot of the frequencies reported at various points in the grid at more or less the same time. So, the time is approximately 11:35. It is not actually measured at the same time everywhere. So, what you see in the west and the east, that is at Mumbai and Kolkata, the frequencies are almost the same. Actually, my statement earlier was that in a synchronous grid, the electrical speeds of all machines and the frequencies should be the same. But of course, it is not strictly speaking true. There are 2 reasons for that. At any given moment of time, a power system is subjected to a lot of disturbances. So, actually they could be small disturbances really, like I shut off the switch of a bulb here, that is a disturbance on the system. So, the system is not strictly speaking in steady state at any point of time. There are always small or large disturbances in the system. So, electrical speeds are not exactly the same if you measure them. But another issue which is probably more important at this point of time is that the frequencies are not measured at exactly the same time of point of time also. So, you may find some differences in the frequencies as measured at 2 places. So, although the western part of the system and the eastern part of the system are a part of the synchronous grid of India, asynchronous grid of India, you will find that the frequencies are slightly different from each other. In fact, if you look at the frequency in the southern part of India, you can look at the slide, you will find that it is different, quite different from what prevails in the west and east, which is not a surprise, because the southern part of India is a different synchronous grid. The nominal frequency of both the southern grid and the rest of the India grid is actually 50 hertz, but you see that the frequency is not exactly 50 hertz, it is around 49.5. So, it obviously means we are not strictly regulating the frequency in India, we allow it to actually change within a band. In a few moments from now, I will also tell you how this frequency is actually determined. I mean, what determines that your frequency is 50 hertz? Obviously, it has something to do with the speeds of the generators. So, let us move on to the topic of today, that is frequency stability in the grid. So, in this particular lecture, I will be covering the voltage and frequency instability phenomena, the control hierarchy in a power system, because there is a need for you to know what are the typical feedback control systems, what are the manual control actions and so on, a bit about the stability criteria and the impact of stability issues on the power system. So, let us move on to frequency stability. You may have guessed that the frequency of a grid, or at least at a particular bus in a simple system like a synchronous generator connected to a load, would be dependent on the speed of the generator. In fact, the frequency of voltages induced on the stator of a synchronous machine depends on the speed of the machine, the electrical speed of the machine. Of course, this particular definition of frequency needs to be modified when one comes to a multi-machine system, because then we will have to talk about local frequency. But let us just first talk about the frequency of a simple isolated system. For example, a synchronous generator connected to a load. The frequency of this bus in steady state will be the same as the frequency, electrical speed of rotation of this synchronous generator. So, if it is a 4 pole 1500 RPM machine, it is effectively going to create EMFs of 50 hertz at this bus, at its terminal. The load is connected at this bus, and let us say we will denote this load power as P L. Now, what determines the speed of the electrical machine? Well, it is determined by Newton's law. It says that the rate of change or the speed of the machine is equal to, this is the mechanical speed, is equal to the difference of torques, the mechanical torque which is provided by the prime mover, and the electrical torque, electromagnetic torque, which is created by currents of the machine. Remember that torque is given by power divided by the angular velocity. The attentive among you would have noticed that there is a minor error here. The torque is given by power divided by the mechanical speed. So, in this expression we should have P m minus P e divided by omega m. So, of course, we have corrected it a few minutes later, but it would be good for you to note this down. Once again, we should have P m minus P e divided by omega m. So, these are the two torques which determine the speed of the machine as per this relationship. Of course, this is the dynamical equation of the machine. If we are in steady state, we will have P m minus P e by omega equals to 0. So, this is only under steady state. So, if actually I have a synchronous machine, say, which is running on no load, that is P L is equal to 0, in that case we will have P E also equal to 0, because in sinusoidal steady state, if you neglect all losses, P L is equal to P E. So, what you will have is that if a open circuit machine which has P L is equal to 0 is suddenly loaded. So, this P E is non-zero before, when you load it, it suddenly becomes, it is 0 initially, and when you load it, it becomes non-zero. What is likely to happen is there will be a sudden imbalance in this mechanical input and the load. If that happens, the speed will change. For example, if P E is less than P m, you will find that the machine, P E is less than P m, the machine will accelerate, or if P m is greater than P, the machine will accelerate, and vice versa if P E is greater than P m. So, the speed of the machine is really determined by this equation. Now, the point is, if P m minus P E is a constant non-zero number, the machine will never reach a steady state, because this quantity here will always be non-zero. Therefore, machine will either accelerate or decelerate constantly. So, what we really need to do is understand how the system reaches an equilibrium. If you want the system to reach an equilibrium, if it starts off with P m not equal to P E, for example, initially let us say P m is equal to P E and suddenly I change the load. So, P E becomes something different. How does this system reach an equilibrium? There are two ways the system could reach an equilibrium. To reach an equilibrium, P m minus P E should be equal to 0. Now, remember that P m and P can be functions of speed. For example, if P E or the load which you put is that of a fan or a pump, it is a function of frequency. So, actually this is a function of frequency. The mechanical power input to the synchronous machine, the prime mover input, also could be made a function of frequency. For example, if I have got a system which changes the mechanical power input to a machine whenever the load changes or the frequency changes. So, both these things could be functions of frequency. So, the final frequency to which a system like this settles down to will be determined by the solution of this equation. So, if we have, for example, a diesel generator set at our home and we connect it to our loads, that is incandescent bulbs or fluorescent tubes or fans or pumps, in that case what we will see is that the diesel generator will have a control system which changes the power when the speed changes. It is called a governor, a speed governor. So, this is one of the mechanisms by which you can attain equilibrium. So, this is as far as a single machine and a load is concerned. What happens when, say, you have got two machines, say a system like this, two machines, synchronous machines supplying a load which is present at this point. So, what determines the frequency or what ensures the frequency equilibrium under this situation? Now, if you have got two machines, you have got two equations. For the first machine, let us say they have the same number of poles. So, things will become a bit easier. Actually, you can use the subscript m1, I think I missed it out in the previous equation. This m denotes mechanical speed. Now, what you notice here is, if I add these two equations, I can write them like this, a little bit of algebra which I am skipping. Pay close attention to this. This is the cumulative inertia of the machines. This quantity, can you recognize this quantity? This quantity may be familiar to most students who have done a physics course. This is called the center of inertia of the system. So, the rate of change of center of inertia of the system depends on the cumulative torques on the system. So, if I want this particular system to be in equilibrium, I should have so what you have here is this. Now, if I am talking of a system which is basically two synchronous machines connected by AC lines and a load here, we must have in steady state why is this so? Assuming that the machines have the same number of poles, what it means here is that the mechanical speeds have to be equal in steady state. That is basically the synchronism condition. We have seen this in the previous lecture, that if the speeds are not equal or the frequencies of the two generators are not equal, you may have a loss of synchronism phenomena. So, what we should have is this. So, which also really means that P m 1 plus P m 2 is equal to P 1 plus P 2. P 1 and P 2 are the electrical power outputs of the two machines. Now, in sinusoidal steady state and neglecting losses, it is easy to see that the total electrical power output of the machines should be equal to the load power. In the previous lecture, I discussed loss of synchronism. Remember, loss of synchronism is when the relative speeds of the machines or the relative frequencies at different buses are not equal. So, you may lose synchronism. Loss of synchronism is basically something to do with the relative speed of the machines. It is not something to do with the common motion or the center of inertia motion. So, let us in our mind have some kind of clarity regarding this. Relative motion stability pertains to, in a synchronous grid, all machines should be in synchronism. So, that is what it should really pertain to. Whereas, common motion, the stability of the common motion is determined by the load generation balance. So, whenever I meant common motion or whenever I have talked about a center of inertia motion, I am really referring to the common motion. So, we have to ensure that machine should stay in synchronism in a synchronous grid, and the common motion also should be stable. So, we should ensure load generation balance. Otherwise, what will happen is you can have a situation where relative motion is stable, but this whole system, the center of inertia of the system is constantly moving. Okay. So, what we should ensure is that the center of inertia speeds in a synchronous grid should be near about 50 hertz. It should be steady at 50 hertz or 60 hertz in some systems. So, what we should have when we have suddenly, for example, load trip. If the load trips in a system, there will be a transient imbalance between the cumulative generation and the cumulative load. So, if there is an existing load and it gets tripped, then you will find that there is a imbalance between the total generation and the total load, and as a result the center of inertia of the system accelerates. So, if you look at the first figure, that is the figure on your left, you will find that as soon as such a disturbance occurs, there is some relative motion and the system frequency tends to rise and settle to another frequency. But of course, eventually all the machines remain in synchronism. So, all the generator speeds tend to become equal after some time. There may be some interplay between them, exchange of power between them, but eventually the system reaches a steady state in which all frequencies are equal, all the generator speeds are equal, and the center of inertia speed equals to the generator speed in steady state. Now, what ensures that it reaches steady state? That is something we have discussed before. Governor action as well as the load frequency dependence, the fact that loads themselves are functions of frequencies, ensure that eventually you reach an equilibrium. That is, if you find a sudden load generation imbalance, the frequency tends to change. As soon as there is a change in frequency, inherently loads like fans etc. change their power output. So, if frequency falls, in fact fans will move just a little bit slower and draw a little bit less power. Similarly, you have control systems like governors, which are present on most prime mover systems, which effectively increase the power, the prime mover powers, in case the frequency goes down, and decrease power in case the frequency goes up. So, this kind of control systems exist on most generators. Of course, the important point is that if you have got controllers which are aiming to keep frequency constant or near constant, they should be coordinated properly. So, that is one of the interesting issues we will discuss sometime later in this course. So, when you have got governors present on many machines, all of them are trying to maintain the frequency at some particular or near keep it almost constant. In that case, you will find that you need to coordinate the governor so that they share that excess power appropriately. So, that is something which we will learn later. Look at the case in which there is a sudden generation trip. If there is a sudden generation trip, the total generation in the system becomes less than the load at that frequency, but as you will find that the machines decelerate, the center of inertia of the machines, which would be somewhere here, will decelerate and then reach an equilibrium based on the governor as the load frequency characteristics. It is important to differentiate this center of inertia motion from loss of synchronism. If there is a large disturbance, this is what the generator speeds may look like. Here you have got one machine whose speed becomes altogether different from the frequency of another machine. So, if you have got a synchronous machines in which synchronous machines are connected by AC lines and there is a large disturbance, you may lose synchronism. So, please differentiate between the center of inertia motion as is evident from these figures, the movement of the center of inertia motion, and the unstable relative motion which is seen in this particular figure. So, this is the loss of synchronism phenomena. Another phenomena which is often seen in the grid because of which could be because of improper feedback controls or the inadvertent effect of some feedback controls is poorly damped oscillations. So, even for small disturbances sometimes you will find that the system does not settle down quickly to an equilibrium. I mean, you will find that it just goes on oscillating and sometimes even these oscillations grow with time in case of certain feedback controllers. So, these are the things which we will learn in this course, but the important point is differentiate between relative motion and common motion. So, common or center of inertia motion is dependent on load generation balance and center of rather the relative motion is rather loss of synchronism is a phenomena in which relative motion is really important. Now, let us just consider a system like this. You have got a generator, it has got a local load, got another generator, it has also got a local load. Say this is supplying 1000 megawatts, let us assume there are no losses for simplicity. This is 500 megawatts. So, this generator is actually through over this line exporting, this is an AC line exporting 500 megawatts, this is say 700 megawatts and this is 200 megawatts. The total load is equal to the total generation. So, the center of inertia is not going to, the speed is not going to change. Let us assume that this is a situation which exists at a particular time and the system is in synchronism and in steady state. Now, because of some disturbance or say a loss of synchronism, suppose the relays trip the circuit breakers at two ends of this line suddenly. So, you have got this line is tripped out. In that case, you have got two systems. Now, you have two separate systems. If the frequency in this system is to remain constant, in that case the generation load would need to be balanced, but look at the generation at this point of time, it is 1000 and 500. So, the frequency will suddenly shoot up, the mechanical power and electrical power are not the same. So, the frequency will suddenly shoot up unless we do something, it will exceed maybe 1 or 2 hertz above 50 hertz, which was say the nominal frequency at the beginning of this disturbance, prior to this disturbance. So, it will suddenly shoot up by more than a hertz. If that happens, this will suddenly, this generator will trip out due to overspeeding. So, this whole island will collapse. So, it is important that as soon as an island is formed, immediately some emergency control measures have to be taken to make this generator, to reduce this generation. So, you need to have governors. Governors should try to reduce this generation quickly. Similarly, in this under generated island, you suddenly have a large amount of load and less generation. So, what you need to do here is strip out the load quickly and increase the generation if you can, again through governors. So, once you island, suddenly you are left with glaring differences between the generation and the load. Moving on to another interesting phenomena which has been observed, that is voltage stability. So far we have been talking about the frequency and relative angle or relative frequency motion of synchronous machines. We will move on to the stability of the voltage magnitude at a particular point in the grid. Now, when does this problem really arise? That is the question we will ask ourselves. Just having low voltage in steady state does not necessarily mean that you have got voltage instability. Normally, if you have got a system, say a synchronous generator, which is supplying some load, let us just talk of a single synchronous generator, so that we do not have to worry about relative loss of synchronism phenomena in this particular system. So, just to highlight the problem of voltage stability, just take a single machine connected to a load. Now, if you have got a single machine connected to a load, if we increase the load at this point, typically it is an inductive load. Most fans and pumps and major loads are inductive in nature, they draw basically some reactive power. So, you will find that there is some voltage drop along the line which carries this power to this point. So, one would expect as you increase the load here, the voltage here will keep dropping. Now, this does not necessarily mean any kind of instability. For example, we will just take this even more simplified system. So, let us take a generator connected via a transmission line to a simple resistive load, something like this. This is E. Now, normally what is the power drawn by this load? You will find that it is E, which is the magnitude. Remember, the phase does not play any role as far as power in this load is concerned. So, we will only talk about the magnitude of the voltage source, E divided by the impedance. This is the current. So, square the current multiplied by R, that is equal to the power in the load. Now, you will notice that the power is actually a nonlinear function of the resistance. So, in fact, P L is equal to, I will just simplify this, E square upon x square plus r square into r. So, this is the power. So, if I change r, power will change. Okay. Another thing is the voltage here, the voltage magnitude here will be nothing but E into R upon this is the magnitude of the voltage at this point. You can verify that this is nothing but V square by R. So, you will get again the same answer if you do V square by R. If I want to increase the power dissipated by the load, so if you got, I will just draw it again. If I want to increase the power dissipated by this load, what should I do? Increase R or decrease R? Well, normally one would expect that if I decrease the resistance, one would get a larger power output. What we will have is power is going to be 0 at R is equal to 0. Do you agree with that? Okay. If I increase the resistance and make it close to, make it very, very large, then also you would expect that the power is again 0. So, what you have is some point there is a maximum to this power. So, what is this point?
So, P is equal to E square R upon x square plus R square. It is easy to show that this occurs when R is equal to x. So, the thing is that in case my resistance value is this and I want to increase the power, what should I do? I should decrease the resistance. But if I am here, that strategy will not work, because if I try to decrease the resistance, my power actually reduces. So, in fact, this is the basic origin of a problem called voltage instability. So, if you look at, say, a load which is not constant but controlled. Suppose I use the rule, I am a very selfish load. I say whatever be the voltage here, I will draw the same amount of power. So, what my rule is going to be is that I want to get the same amount of power irrespective of what voltage appears here. So, what rule I will follow is decrease R if P L is what is lesser than what I desire. So, if I use this rule, I may land up into problems if I am at this point in the curve. So, if I reduce R, in fact, my power will reduce. If my power reduces, I again apply the rule, I again reduce the resistance. My power further reduces, and you will find that you will be driven down, the voltage, the power will be actually driven down and the resistance value will go on decreasing. And it is not difficult to show this. This is the magnitude of the voltage and the power for this particular system. So, if I actually decrease R, power increases, voltage also decreases, but actually V square by R still increases. At this point, this is the maximum power point, R is equal to x. If I decrease R, the voltage drop will be much faster in some sense. I would not say use the word faster. You can say that the voltage drops so much that the decrease in R does not cause an increase in power. So, what may happen is that if you apply this rule, if you have got a control system which applies this rule, you will find that if you go beyond this point, your voltage will be driven downwards. Typically, of course, if voltage goes below a certain point, there are sometimes in many loads under voltage relays which will trip out the load, or the control action will cease at a certain point. But the point is that you have not achieved much by decreasing resistance if you are in this part of the curve. You are actually going to worsen the situation. So, this, if you have got a load which draws power and it changes its resistance or impedance as per this rule, you are likely to have instability if you are somewhere beyond this point. So, this is the basic problem of voltage instability. You may ask, of course, that normally we would design our x to be very small. Why would we normally have an x which is a large value? The answer is yes, normally your x is not very large, and in fact, the possibility of R becoming equal to x is very remote in a normal system. But in case you have, for example, the loss of a large amount of transmission line, distribution lines, in that case you may have a system impedance becoming fairly large. Even more prominent is a situation like this. See, this voltage source which I have shown you here is actually a synchronous generator, and I have shown this as x and this is R. Actually, in a real system, this is how it looks. A synchronous generator is not actually a perfect voltage source. it is a voltage source behind a synchronous reactance. So, actually you may ask the question, is this figure is not the same as this, obviously, unless of course I maintain this to be E. How will I maintain this? See, this figure and this figure convey the same thing if this point here is maintained at a voltage E. But the point is that this E is maintained constant how? By the synchronous generator itself. The field voltage of a synchronous machine can be controlled so that the terminal voltage of the machine equals E, or nearly equal, almost maintained, regulated at E. So, in a normal system, this X is not normally very large, it is never anywhere close to the load resistance. But there is one problem here. This E is not a constant, strictly speaking, it is regulated, roughly regulated by a synchronous machine which has certain limits. For example, what happens when this synchronous machine hits the field heating limit, that is, I cannot increase the field voltage and thereby the field current more than a certain limit. Then this control is lost and I am no longer able to regulate this to E. In that case, it is meaningless to talk of this E as a constant. In fact, this becomes at the limits, this is a synchronous reactance, at the limit, this is how your system is going to look like. So, this is a constant, this is a large impedance, synchronous reactance of a machine is large. This is the transmission line reactance. Now, this system can be prone to voltage stability because this impedance is suddenly very large and this is a constant. Contrast this with this situation wherein the synchronous machine is able to maintain this E by changing the magnitude of the terminal voltage of the machine, that is by changing, I will repeat this sentence. Contrast this with the situation where E is maintained constant by the synchronous machine by changing the field voltage applied to it. So, this is a good situation in which we are able to maintain this E at a constant value, but once the field voltage hits its limit, you cannot increase the field current beyond a certain limit, otherwise it will heat up the field winding. So, there is a limit to this. If this limit is hit, suddenly the picture changes. Here you got a very large system impedance behind a voltage source which is internal voltage source of the synchronous machine, which is practically a constant. So, this can cause a potential voltage stability problem, because the system impedance suddenly becomes very large. Now, you may ask the question, I was talking of a load whose resistance is changing in a controlled way, that is, it is decreasing the resistance whenever the voltage falls down or the power is less than the desired power. This kind of control rule under certain circumstances may lead you to sudden drop in voltage. Now, when does this actually occur? For example, do we have a controlled resistance? Well, you can have a controlled resistance, but a more typical phenomena which mirrors the same thing is this one. You have got a load resistance which actually does not change, but it is supplied from a tap changing transformer. The tap of the transformer keeps changing. So, if the voltage here drops down, the tap A is increased. If the tap A is increased, the effective resistance which the system sees in fact is variable. So, although I talked about a variable resistance, basically a more typical situation is likely to be like this. Of course, the same issues are here 2. In fact, the same arguments are valid here, because this tap A is increased whenever the voltage here falls. If the voltage say falls below 1 per unit here, you will increase the tap. If you increase the tap, the voltage here is like you think it will increase. It will increase to 1 per unit, near 1 per unit, and therefore, the load power can be maintained a constant. But this of course, will not be true if R by A square has exceeded x. So, that is what or rather has decreased below x. So, if R by A square decreases below x, any kind of change in A, the tap, will actually cause a decrease in the power. We will next move on to the other issues relating to stability. They are mainly caused by feedback control systems within the power system, in the power grid. Now, before we look at the control systems which exist in a power grid, of course, that is something we will discuss in the course later on, prime mover controllers, excitation system controllers. You look at the problem in two ways. There are two kinds of things which you normally do in a power system. One is manual actions, manual control actions based on supervision. The second type are automatic feedback controllers. These are the typical feedback controllers which you have learnt in your control systems course. They are used typically regulators kind of, they are typical voltage regulators and governors. These are all automatic feedback controllers. The third thing which you will see is emergency controls. Emergency controls are control actions like tripping of load whenever there is a large imbalance of load and generation. When for example, in an under generated island, one can have a emergency control scheme wherein if the frequency falls, you trip out a load. So, try to get the center of inertia frequency within an island within certain limits. So, this is called an emergency control. In fact, emergency control kind of overlaps with in some way with protection systems as well, equipment protection systems. Now, if you look at the control hierarchy in a power system, you will find that there is at the highest level manual supervision, in which an energy control system center actually looks at the grid, monitors it, suggests changes in power flows in certain lines, for example, by adjusting the load and generation at the two ends of say a transmission line, so that you are not having the danger of going to an unstable situation. So, this is what is, you can say, supervisory preventive control, which a manual or a person in a load dispatch center does, and this may be over a fairly long time. This is also a feedback control. Actually, if you look at the control hierarchy in our system in India, you have got regional energy control centers which coordinate with other synchronous grids. For example, the Western Regional Load Dispatch Center, which is in Mumbai, coordinates with the Southern Regional Load Dispatch Center, which is another synchronous grid. The Regional Load Dispatch Center monitors the overall grid and also sometimes gives instructions to state load dispatch centers. The state load dispatch centers themselves directly communicate with power plant operators, load stations and so on, which is in their jurisdiction. The regional load dispatch center may have a few assets which are under its control, for example, interstate tie lines, centrally owned plants and centrally owned lines. So, this is basically the manual control hierarchy. However, eventually whatever an energy control center say a state load dispatch center communicates with a power station to reduce its power output. In that case, the power plant operator adjusts the prime mover system to reduce the steam input to the turbine, and eventually the generator, the output power reduces, because mechanical power eventually reduces if you reduce the the electrical power output reduces in case you reduce the mechanical input to the turbine. Of course, the energy control center may actually give instructions at a slightly higher level, in the sense they may say reduce the reactive power output of your generator. So, what actually a power plant operator will do is reduce the field voltage, not directly. He may have a what is known as a voltage regulator whose reference voltage he reduces, which eventually reduces the field voltage of the generator, and as a result of which the generator may reduce its reactive power output. An energy control center may also have control over components which are there in the network. For example, a high voltage DC system, you can control the power output of a high voltage DC system, or the reactive power output of certain reactive power compensators within the network. The energy control center may also sometimes do a bit of load shedding in case there is a severe there is a severe generation deficit. So, remember that eventually at the lowest level you normally have a control system which responds to the scheduling orders of an energy controller, a system operator. You look at a typical control system, the typical control system like voltage regulator of a synchronous generator. What it does is it compares the measured terminal voltage of a generator to the reference value. This is set by the system operator himself. It is passed through a controller which may be a proportional controller or a PI controller, and that determines the firing angle of the thyristor bridge, which controls the field voltage which is fed to the field winding of the alternator, and therefore, the terminal voltage is changed. So, if Vref is not equal to the terminal voltage, you may find that the controller adjusts or changes the final output voltage in this fashion. You may also have emergency or stabilizing controllers which modulate the voltage reference so as to improve stability. So, this is something we will learn later in this course. To come to a near important point in this somewhere at the close of this lecture, how does stability eventually affect your system operation? Now, if you are near instability, now of course, this statement itself requires some kind of definition, then a system operator tries to take control actions so as to reduce or change certain parameters within a power system. For example, you may change the power flow in certain lines. So, stability criteria have to be defined much in advance. For example, a system, one would normally like it to operate in a certain way. For example, we would like it to be reliable, in the sense that if one power system component is stripped, the whole system should not lose synchronism or it should not become unstable. So, when a system is operating, a system operator kind of evaluates the stability of the system for certain potential disturbances. So, for example, he may evaluate that if there is a 3-phase fault at this bus at this point of time, followed by the clearing of the lines incident on the bus, will cause this particular disturbance, can cause a loss of synchronism. He will try to take control actions like changing the power flows of the lines which are incident to that bus. This is one possible action. Of course, I am not saying this is the correct action to take, but he can take these kind of actions. So, whenever he sees that any potential disturbance can cause a loss of stability, he will try to change the operating point. Changing the operating point in a power system is done by changing the generation or the load. This has economic repercussions. So, basically stability has got economic repercussions. So, we cannot, whenever you have a system with poorer stability, it is more prone to a fault, and if you want prone to instability, then you have to pay more in order to get a certain kind of reliability, because you will basically try to operate a system which is more meets your stability criteria, and if you do that, you may have to actually move to a kind of uneconomic schedule of power generation and loads. So, this is something of course, we will try to understand later when we understand preventive control. Even while planning, if you find that for typical load generation scenarios your system is unstable, a system planner may have to put in some money and build more infrastructure like more transmission lines, so that for that particular projected scenario the system is stable. So, this even in planning which could be on a long horizon, a system operator has to take into account stability issues. In fact, if for example, your feedback controls in your system are not are causing instability, in that case you may even not be able to operate. For example, there have been situations in the past wherein suddenly almost it appeared spontaneous to a system operator that a system oscillation started building up. You had oscillations in frequency, voltage, power flows because of the feedback control systems which are there in your system. If this occurs actually in practice, it is a very difficult situation, because the system operator may not know what to do if he observes spontaneous oscillations, seemingly spontaneous oscillations in the grid. So, design of feedback controllers, appropriate feedback controllers also involves some engineering costs. In fact, if your system is prone to these oscillations or they have been observed very often under certain operating conditions, you may have to invest time and engineering effort to design or even manufacture proper controllers which will prevent this kind of situation from arising. So, to recap, we have just discussed voltage and frequency instability phenomena by some simple examples. We have discussed hierarchical control and the impact of stability on power system operation. Of course, our last discussion has been a bit brief. We will return back to this topic when we come to emergency and preventive controls later in this course. In the next lecture, we will really start off with the nuts and bolts of this course, the analysis of dynamical systems. Till now, we have been looking at more of an intuitive picture of everything. Einstein had said that the most incomprehensible thing about nature is that it is comprehensible. So, although what we seem to be this course, when we are entering into the nitty-gritties of this course, what we have set out ourselves is to understand the behavior of a large grid, and I mentioned last time it is lots and lots of elements. The point is that by a systematic and scientific attack to the problem, we will be actually able to understand these things rigorously or at least approximately. If not, of course, there is no meaning to perfect rigor in an engineering course, but we will be able to basically from the equations and the models of the system, we are going to be able to understand all these phenomena quite well enough to design controls for them. Thank you, and we will meet in the next lecture.